Okay, so the time is 11:19. It's Monday of the 27th of July. And for today, what I'm going to do is look at different formats to numbers, right? This does include your number system for grade 8s as well for grade 9s. So the idea is that when you guys come out of school, you will have class with me, obviously in class, but however, in the evenings, this is what you guys have to go through. Depending on what you guys actually say in class, right? So if you guys give me the correct answers in class, that means everything is well and macho. But if you guys still have difficulty understanding a few concepts, then obviously this is the video for you guys. So just to begin with, what we have our number system, right? Number system represents all numbers that exist, and to us, it's going to be based on real and non-real numbers. So that's how our number system is in grade 8 up until grade 9, right? However, depending on what subject you take, you might then go to non-real or complex numbers, which you'll then delve in if you go into technical maths. So hopefully everyone that I do teach is going for math, the pure maths, because if you're going to go into complex numbers, they will be done mostly in university, depending on whether you take computers or not. So a science-based subject might need complex numbers. However, for the rest of you guys that will be doing mainly numerical subjects and modules, I would then recommend that you guys take maths. So with that said, let's just get into the video. I've been doing a lot of yapping. So we've got the number system. And for us, we can also call our number system the real and non-real number system, right? Okay, so here we have our number system, and just for a recap, what I will do is start defining what we have in the real and non-real space. So we then have, firstly, I always like starting with non-reals, because from non-reals there's nothing else. It's either you have a non-real number or a real number. However, for real numbers, they then go on and branch out. You'll see what I mean just now. So here we've got non-real. Non-real numbers denoted with an R with a kapi, right? And for that, I'll just pick a different color here, purple. We're going to go for any number divisible by 0. So if I divide a number by 0, any number, it doesn't matter whether it's rational or irrational, but if I divide a number by 0, I will get to non-real. So I've got divide by 0, I've got square root of a negative, I have an x. So all my variables are non-real numbers. Why do I say all my variables are non-real numbers? Because they do not have a definitive answer unless if I solve for x. Hence, I always tell my students that the plan is always to move from your non-real to your real space, especially when you are solving for x. So there we have our real space here, and then I'm going to say here solve for the unknown, right? Sorry, I got a bit of a cold going on. So solve for the unknown. If I'm solving for any unknown, I'm moving from a non-real space into a real space. And then from my real space, I can then classify those numbers as this is going to give me 2 lines. I will have rational numbers, right? And when someone says you're rational, it means you make sense, right? And we're going to say irrational numbers, right? That's how we're going to differentiate the two. So from real, it branches off to what? To the rational. I always start with the good part, and then comes the let's rather put it like this. I don't like saying good and bad. Instead, I like to say normal and not normal. So these are not normal numbers, and these ones are normal numbers, normal numbers that we encounter on a daily basis, things that we can actually measure, meaning you can't really measure irrational numbers because you can't put an irrational number into a cup or a spoon or inside any object that is based on something's size. So these irrational numbers, they don't have a definitive size. Okay, so what we'll do is now we're going to start to define them, right? Let me go for a green there. So I forgot to just denote the letters that we go for, irrational and rational. So for irrational, we've got a Q with a guppy, and for rational, we have what? Just a Q, right? And please take notice, every time we have a guppy, it means what? It means something is not, right? So for rational, it's just denoted as a Q, and for irrational, it's denoted with the Q with the guppy, meaning it is not rational, so it's irrational. Hence, same applies with the real. That's where I noticed my mistake. Real, we've got an R without the guppy, and then for non-real, we've got an R with the guppy. Okay, so let's move on here. So let's go on to defining these two terms, and what I'll do is start defining the easier one. So here we've got rational numbers. Rational numbers, we can just say are numbers that can be written as A over B, where B, right, where B cannot be denoted as 0. If I denote B as 0, what happens? I move on to non-real numbers, right? Meaning that I am no longer in the real space, basically. So that's what we have for rational numbers. Okay, so another way I can define rational numbers, it's a number that can be written as a fraction, right? That's the easiest. Numbers in word form. Numbers that can be written as fractions, right? Oh God. Yeah, my cold is not going to subside. Okay, so numbers that can be written as fraction. So what do you think irrational numbers are? The inverse, right? So if I've got, for my rational numbers, I've got this. Rational numbers, I've got numbers. Okay, let me rather highlight the part that I actually need. So numbers that are fractions, right? Rational numbers are numbers that are fractions. That means that if I were to go and define irrational numbers, I would say that are numbers. So let's just start off with the green first. So we can say rational numbers, let's start with the Q. We can say Q, copy, cannot be what? A over B, right? And here it doesn't matter what B can be illustrated as it, because we cannot have a fraction with them. So we can then say for our irrational numbers, so this guy here, irrational numbers, right? We can then say that there are numbers, still numbers, right, that cannot written English as opposed to spoken English, cannot be written as a fraction, right? So there are numbers that can be written as that cannot be written as a fraction. Okay, so that's a clear definition for both of them. Other mathematicians might define it in a different sense, but that is the closest one that I would say grade 8 and 9s need, right? And then we can quickly look at the examples for them. So I'll do examples in yellow, right? So we've got examples for them. Our examples in this case, we can then say, let's do a bit of rational numbers. So a rational number, let's go for Q. So examples, right? I'll say example one. No, let's just say examples. I can have 5 over 6, right? And 5 over 6 is what type of number? It is a rational number that is a common fraction that is a proper fraction, right? Remember, you have common fractions and mixed fractions. So here the rational, common, and proper fraction. Remember that. It's a key to something that we would be doing in the next round. So here we then have 7 over 3 is also rational. We can have 5 over 1 or even 5, because 5 over 1 is the same as 5. We can even have something along the lines of 5 1 over 3. Now this is what we call a mixed fraction, right? So being able to differentiate the different types of numbers is really important. And then what else do I have? I think that's about it, right? I'll do just those for now. So those are the examples that I'm coming up with when it comes to what? When it comes to rational numbers. What is not a rational number? Okay, so we'll say irrational numbers consist of number 1. I like this one, pi. If you see pi, because it's a continuous number, meaning you still have additional decimals that come up, that means it's still what? It's still going on and on and on and on. If the number goes on and on and on, I can just then say that it is what? Irrational. I'll just quickly go on to my calculator so that you can have a look at what I mean by that. I'll just do my windows there. Okay, that's personal. Windows. Slide over. Let's let it slide over to the right. So yeah, to the right is good. Okay, then let's just have a look at what we get for an answer of pi. So I've got shift pi. Pi gives me a number as 3,141,592, blah 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 blah. So it goes on and on and on. Now the question is, can I get a slice of pie? Okay, I know that sounds weird and funny, but can I get a slice of pie? Meaning, if I had a whole of cake, would I be able to cut up a piece which could be labeled as pie? And the answer is no, because pi is a continuous number. So here we've got 3,141, and it goes on and on, right? Oh, I also forgot, right? I also forgot something that was very critical here, which is recurring decimals, right? We'll get to them as we go. So there we then have pi, and then another one that I can put in here is square root 2. If I put square root 2 in my calculator, let's quickly check what I get. So square root 2, 1 comma, blah, 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 it goes on and on and on. What the computer does is, when I'm calculating using a calculator, it actually cuts it off at a certain decimal point. Meaning, this one is telling me that it will cut off any decimal points at position number 1, 2, 3, 1, 2, 3, 1, 2, 3, 9, at position 12. Meaning, at every number that has decimals that run up above position 12, that's where my calculator will cut it off. But that doesn't mean that there is no other decimals that follow. I hope that makes sense to you. So there we have square root 2. Let me look for one that is a cube. Let's just go for cube. Let's go cube 2. So cube 2, and I'm going to say SD, meaning I'm going to say third to decimal, right? Can you see that part there? Even if I press shift SD, I cannot get a fraction out of it. That means it cannot turn into a fraction. So as well as cube 2, right? So those are just a few numbers I can then mention. But also here, what I want to do is add a recurring decimal. So for this recurring decimal, I'm going to add 0.33. Well, let's just say 0.3 recurring, meaning that the 3 is a continuous. It's a continuous pattern, right? So let's do that in our calculator, 0.3333333 until you see that arrow, right? So I'm going to keep saying that, and then I'm going to say SD. Okay, it's not doing what it's supposed to be doing. Okay, let me just try it again. 0.333333333. Oh, that is a plus signature. Okay, 3333333. Let's say SD. SD. It gives me 3/10. So if I've got 0.3333, it should give me 3/10. Now that's what? That's the fraction form of it, right? I know that you guys use a Casio, so because you guys have a Casio, it's better shown in your calculator, meaning you can just put 0.33 until you get that arrow there. You should see it on the, I think it's the top left corner. Let me just quickly check. No, it's the right corner. On your right hand side of your Casio calculator, you then see that triangle there. That then denotes that you have now entered enough decimals for the calculator to actually process your information. Okay, so now we have spoken about rational and irrational numbers, and I did mention that for rational numbers, they still spread out, right? So what I'll do is I'll just indicate it with the blue here, right? They are then spread out into three different parts, right? Rational numbers are then spread out into natural numbers, natural, whole, as well as integers. I'm running out of space, so we then have integers, right? So remember, if I look at this number system, what I have, I start off with non-real, I go to my real numbers, right? Once something is a real number, it's either rational or irrational. If it's a rational number, that means it can still be what? It can either be a natural whole or an integer. And by the way, it doesn't mean that a whole number cannot be a natural number or an integer cannot be a whole number. It just means that there's a certain limit to what natural numbers are, and it's in the definition, right? So let's insert our new page, and what we're going to start off with is then say that in here we've got rational numbers. Rational numbers are then spread out into three different parts. So we speak about part one. I should have changed this to a different type of paper. Let's change it. Let's change it quickly. Let's change the formatting of this paper. Let's change the formatting. Let's say page, and then let's go for 3-column. I like that. Makes it very good. So good to work with. Thank you. Zoom in a bit. So here I'm just gonna say rational numbers. Just lasso that to the side. Rational numbers. Okay, that's perfect. Okay, and then we said that rational numbers can be spread into three parts. So the first one is natural. The second one is then your whole numbers. The third one is then your integers. Right? So, yes, that's it. Right? Those are the three parts that you need to think about when it comes to your numbers. Right? Your rational numbers. Okay, then moving on, let's define what natural numbers are. First things first, what I'm going to do is just put the symbols for them. So this is then an N, right? The whole numbers one is an N with a kapi. No, sorry, an N with an O at the bottom. That O defines that you can include 0 into your numbers, right? You'll understand what I mean by that just now. And then integers is denoted with a Z, right? Sometimes you guys will see that there are double lines to this, right? It's just textbook form and this is handwritten form. So for your handwritten form, just remember that it's just a regular Z, right? So it's just a Z. Okay, so let's quickly define natural numbers. I'll define natural numbers as numbers starting from 1 to positive infinity. That's it. So it's just thinking about your number line is when you look at numbers starting from number 1, number 2, number 3 up to positive infinity. That's how you then describe natural numbers. And then for whole numbers, we define them as numbers starting from 0 to positive infinity. So what's the difference between natural numbers and whole numbers is that your whole numbers, what I'll do is just do it in a different color. Let's do it in blue. Your whole numbers are all natural numbers including zero, the number 0, right? So that means our limitation starts from where? It starts from 0, goes on 1, 2, 3, 4 up to positive infinity, right? Hence the all natural numbers including 0. And then the final one for integers, we'll say are an integer, or integers are all, let me just let this become small, are all positive and negative numbers including 0, right? I like to view this as a mirror. I think about positive numbers and negative numbers, they're mirror forms of each other. What's the mirror to a positive number? It's a negative number. For example, if I look at 1 does have a mirror of negative 1. If I look at 160, 160 does have a mirror version of it, which be negative 60, right? 160. So that's how you should view them, right? So here we're just saying that these are all your negative infinity numbers, 0 to positive infinity numbers. And that then denotes all your integer numbers. The reason why I'm doing this is so that when I start talking about percentages, when I start talking about what was that? Okay, when I also start talking about finance, all your financial maths, all your ratios, you should be able to have a clear, definitive answer of what your number looks like or what your number tells you, right? For example, if I just think about if you owe someone 150, that means you are 150 to the negative side, meaning negative denotes the opposite of a positive sign. It indicates owing, it indicates less than, it indicates decrease, right? Anything that is on the negative side reflects a not so good answer, right? Unless if you're talking about sickness, obviously, because if I say that you're positive with something, that means it's a very bad thing, right?
for any illness. They say you positive cancer, that means you have cancer, so that's very bad. Let's not think about that. Let's move on. So, those are your integers. From here, what I'm going to do is then go on to today's lesson of numbers and what I want you guys to think about when it comes to this. So, as I spoke about all of these here, I think students should actually have a clear understanding of what an integer is, because your integers play a huge role in your ratios, percentages, in every aspect that you have in terms of changing the format of the number. Your integers are always normally there, right? So for the first one that we're going to deal with, we're just going to talk about fractions, right? What just happened here? We got fractions. Our fractions, let me just say fractions, right? Fractions as a definition there. We've got a couple of them. So I'll start off with common. And then I've got decimal fractions. Yeah. Yeah, that's it. That's it. Those are just the two fractions that we're going to talk about today. So common and decimal fractions. Okay, so with common fractions, I want you guys to think about this. First, you've got common fractions. I forgot the last one. Mixed fractions. Let's rather do this. Okay, it's fine that I put it on the end. It's perfectly fine. So we got mixed fractions. Right? Okay. So for our common fractions, what we're going to do is we're going to divide them into two parts. The first part is going to be an improper, or let's start with proper. Let's start with the good. So we've got proper, and we've got improper. Right? So we've got proper fractions and improper fractions. And the first one, if you think about a proper fraction, what we just say is it's a fraction, because all common fractions are fractions that can be written as what? Can be written as a over b. Hence, all common fractions are technically what? They're all mostly rational numbers. Right? That's what I meant by understanding what a rational number is. And then decimal, right? Decimal are not always rational numbers. They can be what? They're just real. They can be rational or irrational. So we just say real. If it's both rational and irrational, then obviously it's a real number. And then with your mixed fractions, we can then say they're also just real, right? I've never actually, no, actually, they're just rational. Sorry, I've never met a mixed fraction that was irrational. Can't have a mixed fraction and have it irrational as well. So from there, what I'll do is I'll just start explaining what a proper and what's an improper fraction, and then we'll take it from there. So for our proper fraction, we've got, how can we define a proper fraction? A fraction that can be written as a being the numerator, a large numerator, right? Please don't mind my spelling, sometimes I do get things wrong. But the idea is that you actually listen to what I say, and then here we've got a small denominator. Right? So proper fractions are just fractions that are written with a large numerator over a small denominator. That makes it proper. Examples for it, let's go for examples. We can have an example of large would be 5 over 1. As I mentioned, that 5 over 1 is the same as what? Just 5. So technically, if you look at all integers, right, all your integers can be written as a fraction which is divisible by 1. And then that makes it what? A common, or in this, it could be a common fraction. But sometimes it can be an improper fraction depending on the sign. For example, if I put negative 5 over 1, that makes it what? It makes it a small number over a big number. So that makes it what? Improper. So yeah, this is very interesting. Maths is beautiful, guys. So moving from there, we got another one. We can say 6 over 3. It could even be simplified to what? If I say 6 divided by 3 gives me a value of 2. So this is an answer of 2, right? And then moving on here, we could even have 7 over 8. That also makes it a proper fraction. No, I said large. So 7 over 2. That makes it a proper fraction. And then moving on to our improper fractions, we can just denote these as numbers that have a small numerator over, it normally picks up when I'm trying to draw a line, over a large denominator. Okay, and then we can just quickly get a few examples for that. Okay, so I'll say an example of that would then be 1 over 2, which is a half, right? Small over big, right? We can have 1 over 5. We can have 3 over 10, right? Those are then all your improper fractions, right? Another way I could think about this is proper is normal. Now, normal day-to-day, we'll deal with numbers that are normally large over small, and then not so normal, meaning like, for example, if you want to cut something into half, it's not a normal thing. People don't like eating in their house, but yeah, we do that, so we then cut it in half, make it an improper, right? An improper way of giving me cake would be giving me half the cake. It's very improper. You're not being polite. I'm joking. So let's move on to decimals, right? If I move on to decimals, I can just denote decimals as the way mathematicians define decimals is it's numbers with base 10, right? So it's just numbers a number followed okay, let's rather say numbers with base 10, numbers after the comma, right? So that's a clear definition. I'm saying numbers with base 10, numbers or any base 10 number after the comma, meaning we should have a comma with all decimals, right? What I'll do is just give you an explanation about what I mean by that. So suppose I put a number. It doesn't matter what the number is, say 100. So here what I'll do is I'll put integers. So an integer, right, could be positive, could be negative, comma, then followed by what? By base 10 numbers, so followed by other integer numbers, right? So what means by base 10 is meaning here I should have any number that starts from 0 to what? To 9, right? I shouldn't use the comma there, it makes it look weird. So it could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's then your base 10 numbers. So all your base 10 numbers can then follow here, right? So all your numbers here, I'm going to use a negative integer. So negative 6 comma 0 6 7 8, and I'm going to put those dots, meaning it's continuous. It's then a decimal. It could also be discrete. Doesn't always have to be continuous, meaning here I could also say negative 2 comma 25. That makes it discrete. That also makes it rational, right? For a decimal, it also makes it rational. Why am I saying rational? Because we mentioned that here on top, we mentioned that decimal fractions can be either rational or irrational. So let me just show you what I mean by that. If I put 2,25, can you see that I've got a decimal of 9 over 4? So this is technically as negative 9 over 4 in fraction form, right? I hope that answers your question, right? Or whatever you're thinking of currently. Okay, so we're in our last 5 minutes. I'll talk about mixed fractions. Say just mixed fractions, normal numbers, so your integers followed by any fraction, right? So that's how I define it. It's not the actual definition from a textbook, it's just how I would define it in simple terms. So integers with fractions. Integers with fractions attached to them, right? And an example of this would be negative 5 a half. That's then a mixed fraction, right? And I did mention that they are mostly rational numbers. And then moving on from there, we can also say 3, 2 over, no, let's make it 2 over 3, right? And then the final one, what I'll do is just make one that is kind of improper. Well, let's make it proper. So we'll say 4. No, we never make it as proper. We never say large over small. Because remember, the large can always give to the what? It could give to the integer there. So that's a very bad example. So you'd say 4, 2, and 3. Okay, that's about it for this video. I'll see you guys in class. I'll be posting this just now. So when you guys come out, we'll check whether or not you guys understand what we're talking about here.